Find the electric potential due to a solid conducting sphere of charge plus Q and radius A at a distance r away from the center of the sphere for r is greater than or equal to A and r is less than or equal to A. Let's begin with a sketch of our sphere. We have a sphere of radius A, and this sphere has a total amount of positive charge Q. We want to find the electric potential on this sphere at a point outside the sphere. So we will say any arbitrary point outside the sphere, that point might be here outside the sphere. We will call this the distance to this point r. So let's find the electric potential due to that sphere at the point r outside of the sphere. How do you think we should do that? Well, remember, spheres of charge have an electric field surrounding them in space. So this sphere has an electric field that points radially away from the center of the sphere. Because we know the sphere of charge has an electric field, we know that this electric field has the potential to give another charge in its presence a potential energy. So there is a connection between electric potential and this electric field. Well, to discover that connection, let's look at the definition of electric potential energy. Remember, electric potential energy is defined as the change of potential energy between 2 points. And that is equal to minus the work done by a conservative force in moving an object between those 2 points. In this situation, that is minus the work done by the force due to the electric field, and that's given as the line integral of the force and a differential for position, for displacement rather. Well, remember, the force due to an electric field is directly proportional to the electric field, where the constant of proportionality is the charge. So for our problem, the charge is a positive capital Q. This means that the change in electric potential energy between 2 points is equal to minus the line integral of QE. Well, if we divide both sides by the charge Q, notice we have an electric potential energy per charge Q. That electric potential energy per charge Q is what we define electric potential to be. So we now have an expression for electric potential or electric potential difference rather, in terms of the line integral of an electric field. What we are missing in this expression are the limits of integration. Well, by convention, we hold a point infinitely far away to be the point of zero electric potential. So the limits of integration for this will be from infinity to our point R away from the center of the sphere. So in evaluating the potential at a point R, we're going to evaluate the potential difference between that point R and the potential at a point infinitely far away from the center of our sphere. And that's going to be equal to the minus the line integral from infinity to R of the electric field. So let's work with this now. By convention, we set the potential at infinity, point infinitely far away, is 0. So that expression goes away. Also, from Gauss's law, we've shown that the electric field at a distance r away from a sphere of charge is equal to the Coulomb's constant times the charge divided by the distance from the center of that charge to the point at which we are evaluating the electric field. And then the r hat is a unit vector in the direction or parallel to a radial line extending from the center of our sphere. This means that the electric potential is equal to minus the line integral from infinity to r of kq over r squared, r hat dotted with dr vector. Well, remember, a unit vector r in the direction of a displacement differential r is equal to the magnitude of the differential. Now, the reason why this is one version of the dot product says the product of the magnitudes of two vectors times the cosine of the angle between them is equal to the dot product between those two vectors. Well, r hat and the displacement differential have an angle of 0 degrees between each other, and the cosine of 0 degrees is 1. The magnitude of a unit vector is always exactly equal to 1. So we are left with the displacement differential. This means that we could write that the electric potential at point R is equal to minus the integral from infinity to r of kq over r squared dr. Well, k and q are constants, and this leaves us with the integral from infinity to r of 1 over r squared dr. This ends up being minus kq times minus 1 over r evaluated from infinity to r. This then is, well, let's look at it. A minus times a minus is a positive, and we have kq 1 over r minus 1 over infinity. 1 over infinity is just 0. So now we have an expression for the electric potential at a point r away from the center of the sphere, and that electric potential is kq over r, and for this problem, this is for r is greater than or equal to a.